Welcome back to Chapter 1.2, Expectations, Variance, and Covariance as Geometry, Part 5 of 9. In Part 4, we built the variance of a sum, and the headline was the cross term. Now we cash it in. Maya has $1 to split between two assets. Asset 1 is high octane, more expected return, but double the volatility. Everything interesting lives in how the two move together, their covariance. We set up her portfolio variance, then run 3 scenarios at an even split and watch diversification appear. Here is the setup. Maya has $1 to allocate, work in fractions, since dollars scale trivially. Asset 1 has an expected return of 0.08, a volatility of 0.20, and therefore a variance of 0.04. Asset 2 has an expected return of 0.04, a volatility of 0.10, and a variance of 0.01. Asset 1 is the high octane choice, more expected return, but double the volatility. The piece we have not pinned down is how the two move together. Let the covariance be sigma 1, 2. Maya holds weight W in asset 1 and 1 minus W in asset 2, so by the weighted variance formula, the portfolio variance is W squared times 0.04 plus 1 minus W squared times 0.01 plus 2W times 1 minus W times sigma 1, 2. Everything interesting is in that covariance, so we run 3 scenarios at the even split, W equals 1/2, where W squared is 0.25 and 2W times 1 minus W is 0.5. Scenario A. The assets move together perfectly, sigma 1, 2 equals 0.02, the largest it can be. The variance is 0.25 times 0.04 plus 0.25 times 0.01 plus 0.5 times 0.02, that is 0.0225, so volatility is the square root 0.15. The blend sits exactly on the line between the two volatilities. 1/2 of 0.20 plus 1/2 of 0.10 is 0.15. No diversification benefit at all. Scenario B. The assets are uncorrelated, the cross term dies, and the variance is 0.0125, with volatility about 0.112, below the average of the two volatilities. The expected return is unchanged at 0.06. Maya got lower risk for free. Scenario C. The assets move oppositely. Sigma 1, 2 equals minus 0.01. Now the cross term subtracts, the variance is 0.0075, and volatility falls to about 0.087, lower than asset 2 alone, the safer of the two. By blending in some of the riskier asset, Maya built a portfolio less volatile than either ingredient. That is the punchline of diversification. To summarize Part 5, Maya's portfolio variance is the weighted variance formula, and everything interesting lives in the covariance term. Across 3 scenarios at the even split, we saw the full range. When the assets move in lockstep, mixing just averages the risk, no benefit. When they are uncorrelated, the cross term vanishes, and volatility drops to about 0.112 for free. When they move oppositely, the cross term subtracts and volatility falls to about 0.087, below even the safer asset. And through all 3, the expected return stayed at 0.06, only the covariance changed. In Part 6, we stop settling for the even split and find the weight that minimizes risk, meeting the parabola that seeds modern portfolio theory.